Good evening, everyone. Welcome to Network Seminar Series hosted by the Center for Network Intelligence at the ECE and RBCCPS IISc. It is my pleasure to introduce today's speaker, Professor Pravin Nair. He will be speaking on fast sampling algorithms for diffusion and flow-based generative models. Pravin Nair is currently an associate professor in the Department of Electrical Engineering at IIT Madras. Prior to this, he served as a senior chief engineer in the AI video processing labs at the Samsung Research Institute, Bangalore. He earned his PhD from the Department of Electrical Engineering at IISc. He also holds an MSc by Research in Electrical Engineering from IISc and a BTech in Electronics and Communication Engineering from the Amrita School of Engineering. His research focuses on addressing long-standing challenges in image and video reconstruction for both offline and real-time settings, with particular emphasis on developing high-quality, stable, real-time algorithms for image and video processing. Over to you, Professor.
Am I audible? Yeah, okay. Yeah, so thank you for the introduction and good evening everyone. So it's a pleasure to be back here after 4 years, I guess. Yeah. So anyway, in this talk I will be focusing on explaining about diffusion models and possibly why we require to accelerate them. And then one of our contributions, recent contributions, which was a joint work with Anushka Roy. He's an MS research scholar from our lab. Yeah. So going forward, obvious question is why diffusion models? Why is there so much of possibly hype, and at the same time the hype is real actually about diffusion models. Back 5 years or 6 years back when diffusion models came, they were focusing more on image synthesis. How do you generate images, right? At that time GANs were superior. And it solved two problems which GANs had. One is the fact that if you specify a class, for example dogs, right? GANs were getting stuck in one kind of dogs. Okay? It didn't have much diverse, it didn't give diverse images. Diffusion models were able to give that at that time. And then again, the training was much easier. When I say easier, it was quite stable. Same like training deep learning models. You can see the loss nicely decreasing and all those things. Right? Those were the key advantages why all of a sudden diffusion models became very important and people started focusing on that. But fast forward to now, in 5 years, there has been so many different types of work in diffusion models that now possibly the advantages have changed. Okay? It has moved forward, and it doesn't now involve only image synthesis. It also solves very difficult inverse problems. I will show one example. And to the extent that, so usually when we say inverse problems in imaging, people talk about deblurring or increasing the resolution of images, in painting, etc. People have been able to solve medical imaging problems like tomography. It has not come to clinical settings, but there is a good chance. And as far as I know, one of the labs at IIT Madras is trying to bring it to clinical settings, which it has its own challenges. But again, apart from that, even something like solving fluid flow, right? For example, one of the application is there is a fluid flow. Generally, these fluid flows are governed by partial differential equations like Navier-Stokes. One of the application is given some properties of fluid at this time, can I predict some time back what were the properties, right? This is again an inverse problem. Diffusion models are being used even to solve these problems at this time, right? So, to summarize why diffusion models, I think they give high quality synthesis, that is the output, and then strong distribution coverage. You can see some kind of diversity. I will show an example. And then reusable generative framework. GANs had this problem that it had to be trained for multiple applications, etc. Here, domain transfer is quite easier. Okay? We won't discuss much on that, or we won't give more examples on that, but this is back 5 years back in 2021 paper, after which unfortunately people started focusing more on diffusion models and not at all on GANs. Okay, I don't believe that this is the end of GANs. There are people working on GANs as well. The issues with GANs is seen here, ostrich and burger. You see all the images kind of look same, right? This is called as mode collapse. But then diffusion models 5 years back, though the quality is okay, similar to GAN, it does give some kind of diversity. There were a lot of artifacts, right? But the current models, if you see, the best models are Quen image or stable diffusion, etc. These models' quality is much higher than what I have shown here, right? Okay. This is one of the important application which I wanted to highlight, which is kind of surprising. So this is, the right side is my unknown ground truth image. Okay, I don't have that. What I have is the left hand side image, which is measurements, which is getting recorded. Note that this image is highly distorted. There is a lot of blur and noise. Okay. So one of the challenging problem is, can we even try to estimate this ground truth from these measurements alone? And the knowledge of how the measurements are, like what is the kind of amount of blur or amount of noise. That's one question, right? Surprisingly, when convolution neural networks came, it was able to solve to a very good extent, but I would say then attention came and it slightly improved, and diffusion models gave a very large improvement as shown here, right? The third image looks much better, and you have to believe that, this is the only measurement image which is used to restore that, right? And possibly, and possibly some knowledge about the forward model. Okay. But I have shown the time as well, so I wanted to show that there is always a trade-off. Okay, you don't get anything for free. This is 0.07 seconds and 2.5 seconds, and this is a 256 cross 256 image. Okay, currently we are talking about 1000 cross 1000, 1 megapixel or 4K images. Okay, even for this, in a server like A100 GPU, which is a data center server, it takes 2.56 seconds to get this quality. Okay, so it is costly. Yeah.
So how do the size of these models also vary? I'm assuming the DDRM would be millions.
I'll come to that. Actually, the size of the model is the same. Diffusion model based algorithms are generally iterative. Okay, so it is number of iterations into the size of the model which matters, right? Yeah, we'll come to that. No, GAN is not iterative, right? Single model. Yeah. GAN is a single model, actually. That is one of the challenges as well. In fact, there were variants of GANs which was tried to be iterative and they were performing well. But after diffusion models came, not many people work on GAN, so we don't know. Yeah. Right. So even WGANs, the diversity is limited. It's better than GANs, but still the diversity is limited. For example, you can take an open source diffusion model and give one prompt, and there is something called seed, okay, which basically changes the initial point, and you can see the kind of diversity it produces. It's much higher than WGANs, actually. WGAN is better than GAN, agreed. Yeah. So just for summarizing, this is the measurement. We want to estimate ground truth, and we are getting very good images, very close to the ground truth. Okay. Right. So obvious question is, why do we require fast sampling, or what do we mean by fast sampling? Basically, for deep learning model, you train the model and then you infer it, right? You pass the input and get the output. But here, your inference is solving a differential equation. We'll come to that. In fact, in this talk, I will reach there by using the entire description of diffusion models. Anyway, the sampling of diffusion models is an iterative method, and number of iterations becomes very important because in every iteration, we will be evaluating a large network. Okay. The network, I would say, is as large as a transformer-based network which you possibly use for ChatGPT for predicting one token, right? It's as big as that. Okay. So the total time taken here is number of iterations, okay, into cost of evaluating one neural network. Okay. Now that becomes very important because, as I told you, once we train the model, the sampling part or inference part is not just passing the input through the model, it's solving a differential equation. Okay. Yeah, I just want to show the trade-off here, right? So as I told you, it's an iterative algorithm and you can force it to converge in any number of iterations. So here NFEs is short form for network function evaluations, number of iterations. So you see that as we increase from 6 to 20, when the prompt is 2 kids in pink and purple jacket standing by a fence, you see that it requires 15 NFEs to recover the fence. Okay, and at 20, the quality is much better. Okay. So if you don't have a time constraint and if your application can work in a cloud, then diffusion models are really the best. But if you want to bring it to real time or edge devices, then there is a lot of work to do. Okay. There are people working to get the same quality in one iteration or 2 NFEs, which looks like not possible for now. Okay, maybe in future we can. But what we were thinking is, can we at least decrease this by 5 to 6 iterations? So can I get this quality in maybe 6 or 8 or 10 NFEs or 10 iterations? That is that is the problem statement which we were interested, and we found a solution for that. There is still work to do, but I will discuss that. Okay. So till now it's fine, right? Yeah. Okay. So to reach there, to even discuss what algorithm we came up with, first I have to explain diffusion models in detail. So again, every year the kind of discussion I will be discussing diffusion models in a very different way. So I think in 2026, this is the way we should explain possibly diffusion models. So let's try to understand that. If you want to tell in one sentence what diffusion model does is take a clean image, keep adding noise to it, corrupt the image, and possibly after some time you get a completely noisy image from this clean image. Okay, so you keep adding noise in an iterative manner. Okay, then during this process you can possibly come up with this process, and during this process train a neural network such that in the reverse process you take a noisy image, fully noisy image, remove noise in some steps, and then possibly in some iterations you recover the clean image. This is the basic idea. Okay. Now we need to understand what is this forward process. Okay. How do we train the neural network? What is this neural network learning? And most importantly, how do we recover this kind of clean image from this noisy image? That's what we are going to discuss. Okay. Yeah. So let's start. Yeah.
So when that recovery is happening,
yeah.
is it based on a prompt? For example, I take X of capital T, and then I can say recover the cycle, recover the cat, recover the dog.
Right.
It is subject to the prompt that is given?
Yes. So in fact, you can subject to either a class. Okay, you can say that generate a dog, generate an ostrich, which is a class from ImageNet dataset if you are aware. Or you can give a text prompt and then recover an image. So the image has to match with the text prompt. Or you can even, for example, one of the surveillance application has been that given a sketch image, can you generate a natural looking image? Okay, so that also you can condition. So basically we are talking about conditioning the network, right? Yeah. Okay, right. Okay, let's try to understand what do you mean by forward process? How do you explain the forward process, and what is exactly the neural network learning, etc. Okay, so let X naught be the clean sample and P data be the unknown data distribution from which X naught is sampled, and epsilon be a standard Gaussian noise. We assume that it's independent of X naught, and then we have a time interval 0 to capital T, which denotes the corruption time or noise level. So how much noise is going to be added to X naught is dependent or changing according to the T. Okay, let me explain in detail. So the entire forward process of corrupting a clean image with noise is designed in advance through user decided schedules or functions st and sigma t. Okay. So st decides how much amount of clean signal should be retained at time t, and sigma t is how much noise should be added at time t. Okay. So xt equal to st x0 plus sigma t epsilon. Okay, this is the equation which people generally use to corrupt an image. Okay, it's pretty evident what we are doing here. So conditioned on the clean sample, okay, only epsilon is random. So xt's distribution has mean st x0, xt has mean st x0, and covariance is isotropic sigma t square. This is our choice. Okay, there is no need to be isotropic. This is easy to handle. So people use an isotropic Gaussian here to add. Right. So conditional distribution of xt given x0 is given with mean st x0 and variance sigma t square. This much is clear. Right. Now how do you choose st and sigma t? Right. As we said, we are trying to corrupt a signal or image to form a noisy image. So at time t equal to 0, your s0 is 1, and time t equal to capital T, your st or s capital T is 0. Okay. So here at time t equal to 0, you want your xt to be equal to x0, and time t equal to capital T, you want your xt to be epsilon, which is standard Gaussian noise, approximately. Okay. So given a data point, schedules decide, these functions decide how the trajectory should be. Okay, I want to point out that you are picking a sample, data sample. So for every data sample, the trajectory will be different because you are adding a random Gaussian noise as well. Okay, remember that. For every time you sample a Gaussian, the trajectory will be different. Right. So these are some of the standard ST and sigma T's being used here. So I am not going to discuss flow models separately because all this come under same framework. Flow models make sure that your ST and sigma T is linear. It considers that noise is added in a linear manner as time progresses. But these two, the diffusion models, is basically trying to add noise much more like in a linear manner in the starting time, and at the end it's fine, it's all same. Okay. So I think it's intuitively makes sense, right? As when you start, you add small noise, and then when you end, when time t keeps on going, you keep adding more noise, okay? Or less noise rather. Right. Here there is a less noise added. The noise variance difference is quite less. Okay. Right. Okay. So, so far we are talking about forward process, nothing interesting till now because we have just told that you give me a time t which belong to 0 to capital T and I can give a noise image corresponding to it. Right. But image generation asks in opposite direction, right? It's asking for that if you can give me a noisy image, how do I recover clean image from it? So it's the opposite direction which is being asked. Like GANs, obvious question is why don't we directly map from x capital T to x0, complete noisy image to clean image. Okay. It's already clear there is too much of information loss that it becomes very difficult to train a neural network or whatever, however your training mechanism is, how much ever data samples you have, you cannot really recover from x capital T to x0 using one network. And that in fact was one of the disadvantages of GAN. Okay. Right. So, image generation, at least in diffusion models, proceed very carefully time step by time step. From x capital T to x0, it takes a sampling interval of tau, xt to xt minus tau, t minus tau, and till then x0, right? But how do you do that is a question. Okay, yeah. So rather than requiring a direct map from x0 to x capital T or x subscript any t in 0 to t, what we are asking is, if you give me a noisy image xt, I want to recover a noisy image at xt minus tau, so backward. If I can come up with a mechanism to get this, then x capital T is a standard Gaussian noise, sample a standard Gaussian noise, and then use that mechanism to come one tau sampling time step, like tau's time backward, right? T minus tau, t minus 2 tau till 0. Okay. So in effect, again I want to point out, I'm talking as if these are images sampled from some distributions. Okay. So this is a stochastic process, and at every t you have a marginal distribution corresponding to it. Okay, I am telling marginal because till now I have been talking about xt given x0 conditional distribution. Right? Yeah. So the question is, how can we find how to find the sequence of marginal distributions pt minus tau to p0? Okay, this is what we are asking. Right. Oh. Right. So one obvious point is we have been straightforward and we were trying to get xt given x0, but what we are actually asking is, given a noisy image at one time step, you want to find the noisy image at the next time step. That is the forward process. Reverse process is, given the noisy image at xt, you want xt minus tau, right? So obvious question is, how do we come up with distribution xt given xr where r is less than t? This is the forward process, right? That's not clear. Just because you have come up with a Gaussian process or a stochastic process to get xt from x0 doesn't mean that you know how to find xt from any xr such that r is less than t. Okay, I'm basically hinting at Markov process. Can I come up with some understanding of when this process is Markov, right? It depends only on the previous time step. Right. So all we have is this is what we defined, it was our choice. Then we are asking, how do we find the distribution of xt given xr where r is some previous time step? Okay. If it's a Markov process, it means that it doesn't depend on any of the time steps before that. Yeah. So equivalently, let's try to do this math like calculations, and we'll reach a place where we'll get the condition which is required for this stochastic process to be Markov. Okay. We assume that it's Gaussian. That means xt given xr is Gaussian. So your mean is at/r xr and your variance is bt/r. Okay. Let's try to calculate that. It's a very easy calculation. We know xt given x0 and xr given x0. Now we have assumed xt given xr to be Gaussian. So obviously expectation of xt given x0 should be, if you substitute xr in terms of x0 here, it's easy to find that expectation of xt given x0 should be AT r SR. Right? We have already defined it to be ST x0. So from this immediately you get AT/r to be ST by SR. Right? It's pretty obvious. And then covariance, we get it as AT r square sigma r square plus BT/r square. So I hope it's clear. I'm just trying to substitute XR in terms of x0 here. Okay, that's what I'm doing. So covariance is given by AT/r square sigma r square plus BT/r square. From this you get an equation for BT/r square sigma t square minus ST square by SR square sigma r square. Right? So therefore xt given xr has mean ST by SR into XR and this variance or standard deviation. I hope the condition is clear from here. This thing should be non-negative, right? This expression. So that's the condition. So when you are choosing ST and sigma t, make sure that this condition holds so that it's Markov process. Okay. Let's try to understand what this condition is. The variance is sigma t square minus ST square by SR square into sigma r square. If it is greater than or equal to 0, then you get this. So if noise to signal ratio is given by sigma t by ST, then it says that noise to signal ratio is non-decreasing. Okay, it's greater than rho r, or in other words, as we all know, signal to noise ratio should be non-increasing, right? Which makes sense. So it says that when you are adding noise, you should make sure that signal to noise ratio is non-increasing as you increase the time. Okay, so noise has to be gradually added in that fashion. Okay, so this is the condition for your stochastic process or forward process to be Markov. Okay, okay, right. So this is what we came up with. Now we know that given xt plus tau, okay, you started with two schedules, right, two functions st and sigma t, just to go from x0 to xt for any time t between 0 and capital T, right. From there, under some condition, which is a very reasonable condition, we understood that this is a Markov process, and now we know given xt how to move to xt plus tau. Okay, so we know that the mean is st plus tau by st/xt, and this is the variance, right. So one of the problem with what we are doing till now is we are discussing too much with discrete time steps, right. We are almost thinking that tau should be fixed before, etc. We want more flexibility. So generally when you are working with discrete time steps in any kind of algorithms, if you want more flexibility, you try to understand the continuous version of it, right. So in effect, you have to make sure that the tau tends to 0, right. And it so happens, I'm not going to discuss this in detail, if tau tends to 0, this is equivalent to a stochastic differential equation. I will intuitively explain what this is, where you get the dynamics to be defined as dxt, change in xt, is given as f of t into xt. This is why it's called linear. It's f of t into xt. This function is linear in xt. dt plus some Brownian motion, g of t dwt. What does this mean, right? So Brownian motion, I hope people know about Brownian motion. This has this nice property that the increments are Gaussian, right? And increments are Gaussian and its variance is equal to the time difference. Okay. So suppose del wt equal to wt plus tau minus wt, because we are talking about only tau change, right? T to t plus tau. Then we get del wt as root tau epsilon, or this which is standard Gaussian. Right. Now if you want to discretize this with dt being tau, this is xt plus tau minus xt, which is given here. F of t x tau, f of t xt, dt is tau and g of t, and del wt is root tau standard Gaussian, right. So you see, this is nothing but if g of t is 0, this is an ordinary differential equation. dxt by dt is f of t xt. So this is just that while discretizing, you want to add some noise to it. Okay, if people have heard about Langevin sampling, you can connect with that as well, right? So now if you want to add noise at every iteration, every step, that ordinary differential equation becomes stochastic differential equation with g of t. Right? So if tau is greater than 0, you get this discretization. Now you need to make sure that tau tends to 0, and for that you have to find f of t and g of t. You can match this and this. Right? How do you do that? If you want to make tau tends to 0, st plus tau can be written as st plus tau s dot t, right? And then you have to make small of tau. Right? That's the entire idea of this, right? I'm not going to do the calculation, so I will just match f of t and g of t and tell that if you want continuous version of this Markov process, what we have done here, it's given here dxt equal to f of t xt plus g of t wt, where f of t and g of t is given in this form. So f of t involves s dot t by st. Okay, s dot t means d by dt st. That's what I'm st dash, right? And g of t square can be written as 2 st square rho t, which is noise to signal ratio. That's why noise to signal ratio becomes important. And rho t dot, okay, d by dt rho t. Now g of t square has to be non-negative, right? It's a square term. That's possible because we started, okay, with this assumption that noise to signal ratio is non-decreasing, right? So obviously rho t dot is greater than equal to 0. So it's valid. Okay, so you have to, it's consistent. Whatever we are deriving is consistent with this Markov process. It's using the same equation. Right. Any question till now? Right. So what we have done now is, still we are in forward process. We have not gone to reverse process at all. We have, we came up with st and sigma t, two functions, how to retain the signal and how much noise to be added at every time. From there, we have derived this stochastic differential equation, which is our forward process. So the entire forward process can be explained using this differential equation, right? Okay, good. So given xt, I now exactly know how to move to xt plus tau, but generation is reverse, right? Given xt, you need xt minus tau. Okay, so xt minus tau, xt minus 2 tau to x0. So we need to find this reverse conditional distribution xt minus tau to xt minus tau given xt, or equivalently dynamics, right? Whenever you have a differential equation from which can be the trajectory can be got from 0 to capital T, to reverse it you integrate capital T to 0, right? That's what you generally do, right? Either way you need to solve this. One of the problem very clear is that just because you know q of xt given xt minus tau, which we derived just 2 slides back, you don't know the xt minus tau given xt distribution. This conditional distribution you don't know because these marginal distributions are not tractable, right? It depends on x0. We know only the conditional distribution of xt given x0 or xt minus tau given x0. We don't know the marginal distribution of xt or xt minus tau because data distribution is unknown, right? So analytically we have no idea what those are. So it's a difficult problem. Just wanted to point that. Another way is we came up with this stochastic differential equation which governs this. Yeah. Yeah.
Can't we say that the term about the numerator is also intractable because we don't know the denominator? It can be written as the term that is in the denominator. So pt xt, this term.
Yeah. So t minus tau is backward. So maybe ptxt can be written in terms of pt minus. For now, we have not come up with the reverse part at all. Right. Till now, what I have explained, I think at t you can write it in terms of t minus tau. Yes. Reverse part. This is what we want to find, right? Yeah. So you can write ptxt, but either way, I mean, even this term is not tractable because if you write it as an integration, it is xt minus tau given x0, which we know, into data samples probability and integrate over all the samples, right? So we don't know the probability of the samples, so it's intractable. That's my point. Okay. Yeah. Any question till now? Okay. So obvious question is, now we understood that forward process is an SD, stochastic differential equation. Let's reverse it, right? Let's try to understand the basic part, ordinary differential equation. Reversing is very easy for ordinary differential equation. Suppose your dxt by dt is some velocity field and you start x0 sampled from your data distribution. No. So starting from x0, your forward integration gives xt1 to x capital T. You can choose your time steps. Okay, and xti equal to xti minus 1 plus integration of this velocity field from ti minus 1 to ti. Okay, all your solvers, ODE solvers, basically try to approximate this integration. That's what they do, right? And recovering back, okay, or the reverse integration is pretty easy, because you can directly integrate from capital T to capital 0. Now introduce this tau, which is capital T minus t, and come up with a new state variable y tau, and then you can write it as dy tau by d tau is equal to minus v. This is a pretty simple calculation. In other words, reverse integration is just changing the sign here, plus to minus, that's all, right? For OD, it's pretty obvious. When you go forward, you just have to integrate from ti minus 1 to ti and add it. When you come backward, you have to subtract that. That's the entire point. The problem comes with SD. It's no more the same. Obvious question is, what do you mean by this reverse integration, right? Here, you start with an x0, a data sample, and go in a trajectory. The trajectory is fixed. It's deterministic. There is no randomness involved here. Okay. So here the question is, if I go from x0 in a deterministic fashion and reach x capital T, can I come back from x capital T in a deterministic manner and reach x0 with same time steps, right? There is no randomness. So it's pretty easy to even explain what it means by reverse process, right? Yeah.
Maybe it's a type of, you can't write x0 is coming from distribution p0, because in this case you also want to match the marginal side of the situation.
Right.
In the ODE.
In OD, I really don't.
Maybe it's just supposed to be x and 0 is equal to x0.
Yeah, that's all. Yes. So x0, so that's why I'm overloading here, right? x0, because x0 at time 0 it's data sample, right? Yeah. But one of the question is, what do you mean by here reverse integration, right? Here now, because we are adding noise at every time step, there also it's a random variable, here also it's a random variable, but then it changes, right? Because it depends on how you are doing the forward integration, okay? From OD, it looks like we could have directly written a minus sign here, minus f of t xt minus g of t dwt. It doesn't work, because this dwt is a Brownian motion, and you cannot use any more ordinary calculus. If you see here, we have done integration, etc., right? Integration uses calculus, but once you use Brownian motion, you cannot use your ordinary calculus. You have to use something called Ito calculus. We won't explain. But then how do we check whether we are reversing properly or not? Now, here given an ODE for forward process, I gave another ODE for reverse process. Okay, you check by checking the samples whether they are matching or not. Here you can check by matching the marginal distributions, right? So if you start with x0 and move forward, at every t you have a marginal distribution. Now that marginal distribution should match with whatever reverse SDE you are coming up with, right? That's the point. You can try it out. If you write here minus f of t xt and minus g t dwt, those marginals don't match, okay? And that comes from the fact that this dwt is a Brownian motion. More interestingly, you have something, yeah. It's too much actually. Yeah, I will show you how far. I mean, it will be clear when I write the actual reverse SD, how far it is, right? Yeah. So anyway, one interesting point of view is that even to come up with reverse SD, you require a different concept, which is called score function. It's a very intuitive function. So S star x comma t is gradient of x log ptx. Okay. What it means is that the gradient gives you the velocity or the direction in which the probability distribution increases. Right? So if you see this is my pt of x, then this dark area is the one which is having high probability. So if you see at every point, it's giving you the direction to move towards this high probability. Right? So score function is actually a velocity field which tells you the direction at any point to move towards the high probability areas. Yeah. So it's more, it comes from, ease of handling, right? Probability distribution log, it's between 0 and 1, you take a log and do that. But other than that, I would also say that it has like connections with KL divergence, score functions, etc. Right? Yeah. So it's a choice actually. I don't see a reason why we shouldn't have numerically. Only reason I feel is numerical, at least in this case. In other cases, no. Right. Now I want to tell about reverse SDE, which should match the marginal distributions in this case, right? So this is a stochastic differential equation, and because of this, at every t there will be a marginal distribution, and it so happens that the reverse SDE has a score term as well, right? So here the velocity field, is f of t xt. This is called as drift, and g of t is called as diffusion term because it's a scaling of your diffusion. So g of t basically changes the variance of this, right? So here the drift field has f of t xt and a correction term which comes because of this Brownian motion, and this correction term comes in terms of the score function. Okay, you can easily actually, this proof is very easy. So what you need to do is just try to understand what the marginal distributions of each at t should be, and you match these two. You will see that when you integrate this particular stochastic differential equation from capital T to 0, the marginal distributions match for any eta of t greater than or equal to 0. Okay, eta t can be any function. So unfortunately, like ODE, you cannot reverse SDE by putting a negative sign. Okay, so this term comes in between, and now we have this extra problem that we need to estimate this, right, score function if you want to reverse. Okay, that's the problem with diffusion model. That's the problem with what we have created, forward process. Right. Any questions till now? Yeah. So just want to point out, even with the exact score, all the dynamics varying with eta will have same marginal distribution. Okay, that's all I am claiming, same marginal distribution. If eta t equal to 0, you in fact avoid this term and you get a nice ODE, it's called as probability flow ODE. And if you see all the state of that algorithms or in diffusers library, they use only this because all they want is to compute marginals. So they really not care about this term unless it's required for some application. Okay. For inverse problems, you require this. Okay. Just wanted to point that out. Now, if you have this reverse SDE, if you have score function with you, okay, ready-made, then it's very easy to find from x capital T to x0, right? At time t0, sample from the standard Gaussian, okay? Then every ti may be equal to t capital T minus I tau, that is you are going in tau sampling time, right? T minus tau, T minus 2 tau. Maybe tau you can take T by 1000 or 100 or 10, whatever you are comfortable with, right? That many iterations will be there. And then xt I plus 1, that is xt minus tau, can be got from xt I by just discretizing this part. Okay, this part discretizing is pretty easy. We have already seen how to discretize an SDE, right? dwt for a tau interval will be a Gaussian, standard Gaussian with some variance, right? Variance will be tau. Right? Now here the variance will be g of tau, g of t into tau. Okay, yeah. So it's pretty easy. If you know the score function, it's pretty easy. You just have to discretize this SDE, right? But the problem is we don't know the score function. Okay, we'll come to that. I wanted to show this part as well. Again, I want to point out that here we are discussing about marginal distributions and the way the trajectory is formed. So sample paths for this process also become very important. So here this is forward SDE. So there is a velocity field f of t xt. Unfortunately for reverse, the velocity field changes. Both these are different because now score function comes into picture, right? And if you have the same velocity field, either you can have a stochastic trajectory, I mean random trajectory. That's why there is so many, zigzag lines here. Or you can solve this nice probability flow ODE which doesn't have any randomness. Okay, eta t equal to 0. It's up to you. Okay. Point is, same marginals doesn't mean same trajectories. It depends on how every step is formed. Okay, whether you are adding noise or not. Okay. Right. Maybe we can talk this outside. Right. Okay. Yeah, I can discuss that actually. So, yeah, Langevin sampling. It's like how stochastic gradient descent and gradient descent are related. Right. You add some noise to have that. So here this diversity. So you add noise so that there is some kind of diversity in trajectory. Otherwise, what happens is you choose x capital T from standard Gaussian and then solve the ODE, you are going to get a deterministic path. So the only way, for example, if you fix a prompt, the only way you can get different paths is by sampling different samples from Gaussian, right? But here now you have more variety, and this variety is important in some cases, because you see when you want to a dog sitting in a park, right? You can think of so many types of images which can come in mind, right? So if you want that much of diversity, then you should possibly add some noise at every step, right? So that means eta t should not be 0, it should have some value. Okay, that's the idea. Yeah. Okay. So with exact score we are done, right? Reverse time SDE or probability flow ODE, you just need to discretize from capital T to 0. But again, the problem is we don't know the exact score, because the score function is given by gradient of log of ptxt. Again the same problem, marginal distribution. We don't know the marginal distribution, right? We know only because it's not tractable, right? We don't know the data distribution. What we know is this pt of xt is integration conditional distribution xt given x0. This we know because this is what we started with, right? We started with the forward process where the conditional distribution was fixed by st and sigma t, right? Okay. This guy we don't know, data distribution. So neither ptxt, marginal distribution, or the score function can be evaluated analytically. So we need to come up with an approximation. Every time we use Monte Carlo, right, to come up with an unbiased estimate whenever such kind of problems come up. That's what we are going to do as well, right? Yeah. So we know q0 to xt given x0. So the score function del x log ptxt can be written as 1 by ptxt del xt ptxt. This is pretty obvious because of log function. And ptxt we have already seen here what is the integration, right? So I have swapped the gradient and the integration. It's absolutely not obvious. Okay, you need dominated convergence theorem, but for now I'm assuming you can swap it. Okay, so after this you can write your del x q0 t xt given x0, that is the conditional distribution's gradient, as the distribution multiplied by score function. Okay, now here we have brought conditional score into picture. Okay. Now bring the ptxt inside. So you get this part. Now you obviously use Bayes rule, and you get your score function as integration of the conditional score multiplied by probability distribution of x0 given xt, right? Let's try to understand what this means. So therefore your score function has to be evaluated at a point xt, right? Score del x log pt xt, right? So what do? Given an xt, you try to see which all x0 can reach xt. Okay. For all those x0, find the score function and average, conditional score and average. That's what this says. Okay. Is this clear? So we don't know how to find score function. Even this we don't know because we cannot estimate how many x0s can reach xt. But at least I hope you all understand what will be the next step, right? So what I have done here is the main score function, which is very difficult to estimate or not possible, not tractable. We have written it as average of conditional score given a noisy state xt. Now this we have chosen stx0. So finding the score is very easy, xt minus stx0 by sigma t square. So log, here log helps, okay, because log is there, you got rid of this exponential and then you take the gradient. So you get this nicely as xt minus stx0 by sigma t square, okay, right? So if you have access to clean samples, okay, we could pick a t uniformly between 0 and capital T and epsilon from some standard Gaussian sample, and then you can find your conditional score at least, which is given by minus epsilon by sigma t, same as this too. So both are same. Minus xt minus stx0 by sigma t square and minus epsilon by sigma t. Right. Okay. So now you have written score in a very weird way, but yeah, interesting way, because you pick some sample and then try to estimate this minus epsilon by sigma t. So if you can pick one data sample, highly unbiased, but minus epsilon by sigma t is an unbiased estimator of your score function. Okay. So it says that if you have clean image with your hand, in your hand, you can possibly add at time t SD x0 plus sigma t epsilon. Whatever xt you get, for that you can find the score approximately by using an unbiased estimate. Okay. So you cannot do it reverse. If I give you xt, it's difficult, but at least you can do this part, right? For different xt's, you can generate xt and find the unbiased estimator of score function. Right. Is that clear? Any questions here till now? Yeah. But again, right, all till now we have been talking about forward process and we were assuming that we have clean samples in our hand, right? For image generation, you have to generate the clean sample. You don't have x0 in your hand, right? When such kind of cases happen, that's where you use neural networks basically, right? So you see in forward process, you have a way to estimate the score function, del x log ptxt, at least in forward process. Okay. In reverse process, you don't have a way because this forward process, whatever estimate we generated is conditional on the data sample, right? In reverse, we don't have because we are trying to synthesize a clean sample, right? So what do? We learn a neural network, right? We learn a neural network which takes xt and t as input. Okay, that we know because if you think about it in reverse process, every xt and time we know and we want to find an xt minus tau, right? So with that as input to the neural network, you try to regress the target epsilon by sigma t minus epsilon by sigma t, which is a highly unbiased estimator of the score function of xt at xt, right? Yeah. So during generation, you approximate your score function with s theta xt and you replace here by s theta xt. Okay. Then your reverse process or image generation converts to discretizing this process, reverse SD. Right? So you have got an approximate stochastic differential equation which should be used for image generation. Any question till here? Right? Yeah. So just want to recap. We started the forward process by finding ST, like by choosing ST and sigma t. Then we showed that it's a Markov process. Then we also showed that it corresponds to a stochastic differential equation. Right? This was the forward process. Now if you have any differential equation, any reverse direction, how to integrate is basically reversing the dynamics of it. So we were trying to integrate or reverse the SDE and we found that we came up with a problem that it involves score function. Right? Then the problem turned into estimating the score function, which we were able to estimate given clean samples. That means only during training when we have access to clean samples, you can estimate the score function, which is used to solve the reverse SDE. This is the idea, right? Which we don't have in image generation. So we learned a neural network to regress that score value. Right? This is the recap till now. Any questions, please ask. I just given the training algorithm. This is the interesting part. Okay, there is some engineering going on here as well. So let's go through this one. We sample a data, we get a data sample from our data set. You pick t, which is uniformly sampled between 0 and capital T. Okay, sample a Gaussian noise, right? Epsilon standard Gaussian noise and construct xt. Now you know an estimate for score function which is minus epsilon by sigma t. So you find this loss function s theta xt plus sigma epsilon by sigma t and then you update the neural network parameters, right? An important issue with this is no one uses this because when t is near to 0, you see epsilon by sigma t blows up, right? It's huge value. So you cannot train a neural network to learn this properly. Okay? So one of the engineering trick which people do is instead of learning s theta xt comma t, they learn noise directly, epsilon theta xt comma t, and your score is minus epsilon theta xt comma t by sigma t. Right? So that's one assumption which is done, and here it is nice because it's Gaussian noise. So it's nicely bounded, so training is much easier. Okay. Yeah, just wanted to point this out. Okay, I hope till here it's clear, right? Now coming to our work, we need to understand how do we do this image generation by solving the stochastic differential equation or this ODE. I'm going to explain only the ordinary differential equation part. The other part is kind of obvious. Anyway. So our ordinary differential equation to be solved is dxt by dt f of t xt term and this core function term which came in extra, right? So with noise prediction, it just changes to epsilon theta xt by sigma t minus goes off. So this is my ODE to be solved, right? The problem with this ODE is that people were not able to get high quality images when number of iterations, or now you know, right, number of time steps. So when I say 6 time steps, all you are allowed to do is 0 to t divide into 6 sampling intervals, right? Okay, 10 means you can divide it into 10 sampling intervals and go from t minus tau, t minus 2 tau and so on. So this ODE can be integrated in reverse. Okay. Any question in this? Yeah. Right. So there exist some methods. Okay. Many of the methods which are used by fast solvers either take 20 plus or 10 to 20 iterations. The ones which use 6 and 20 either don't give images very well or are extremely complicated, so much that they have given the code but we don't know how to adapt. There are many coefficients to be estimated and it uses highly stabilized RK methods which are kind of difficult to even understand, leave alone adapt the code, right? So we were asking this basic question. I mean, it's at the end it's just an ODE, right? Can we come up with intelligently realized some algorithm which is simple, adaptable to different models? When I say different models, you might have heard about stable diffusion, Quen image, etc. Right? There are 10 to 20 models which are very famous. Okay. Now, using those models, that is core functions neural network or noise prediction network, can we just have a simple algorithm which can be used to generate image? That was what we were trying to understand. Okay. There comes the first thing which we started asking is why is 6 or 10 very difficult, right? It's actually very intuitive. Here I have shown a vector field. Okay. When you allow your 100 steps, right? The time step or tau here, which I discussed, is very small. So your vector field is a very good approximate. You can go in that direction, right? So Taylor series basically, first order Taylor series is good. So all of them are connected to Taylor series, right? How do you discretize, etc. So if the time step is less, your vector field or the velocity field is a very good approximate and integrating becomes easy. Remember, ODEs, every time step discretizing is basically approximating integration. I showed that, right? But once it goes to high step, right? If you go in this direction, you will be predicting this as xti plus 1 instead of xti after xti. But the true one, because of the vector field change, might be somewhere else, right? So there is a good enough gap here. So what we are asking is, can we estimate this gap, approximate this gas and correct this prediction? Right? That's what we are asking. Right? In ODE theory, it's very, very well known. How do we correct? There are many solvers where first predicts and then corrects. So that's the idea. So if we want to come up with a solver which can work with 6 or 10 steps, we need a mechanism to correct them. Right? Yeah. Okay. Again, what does low NFE, why low number of iterations is difficult? As I told you, we are approximating this integration. Mostly we use Taylor series, and Taylor series only works if your step size is less. So it's very difficult. And then it's an iterative algorithm. So errors are accumulated. First step there is some error that gets accumulated and so on. So you need to correct at every step. Okay, then only you can possibly reach the data sample. Another problem which is more to do with diffusion model is that here velocity field, if you see here, the velocity field is f of t xt minus some s theta or epsilon theta, which is a neural network, right? So you are not allowed to evaluate the neural network multiple times during one iteration. That will increase the time, right? There are many solvers which does that. Hune, RK, Ranke-Kutta methods and all those methods work by possibly estimating at ti plus 1 by 2 in the midpoint and then try to estimate properly. We can't do all those things because if you try to do that, then the time increases, right? In one iteration, you can do only one inference of or one evaluation of neural network. That's the problem. Yeah, I hope the issue is clear. Okay. Yeah. So the method which we proposed is actually like any other ODE solver, very simple. First do change of variables, then predict it, and I told you that there will be an error, then correct the error. So most important part here is correction. How do you correct? Okay. Remaining things are pretty much easy. I mean, there is nothing novel there. Right? Yeah. So it's specifically designed for this challenging 6 to 10 steps and no additional neural network evaluation. One step means one neural network evaluation only. And very small implementation overhead. I think this is the most important. You give me any diffusion model which is trained anywhere, I can easily plug it into this algorithm and generate the image. Okay, right. Let's go step by step. The first step, you come up with this ODE. Okay, I have replaced here into rho t dot. Okay, the velocity field here has a linear term in xt and some non-linear term. Rescale the state by st and form yt. In yt, the dynamics becomes much easier. I have removed the linear part completely and now only non-linear term is there. Right? More importantly, again, your non-linear term is epsilon theta, which is trained to regress your Gaussian noise. Okay? So it's nicely bounded. Okay? It's very nice. The target was nice, right? It's Gaussian noise. So this matters actually. If your velocity field is too, the range is too high, etc., you apply any solver, the variations will be too high and you will have a lot of numerical error. Okay? So this helps, right? So linear term has disappeared completely, but one point to notice, your T0, T1 to T capital N might be uniformly spaced, but the row points might be non-uniformly spaced. Okay? So you have to come up with a solver which can handle non-uniform step size. You cannot fix and tell that tau, it should move only with tau. Okay, it can be tau 1, tau 2, etc. Okay, then use a higher predictor. There is nothing novel here. Okay, so your Euler method to solve an ODE, basically take your neural network output at I, epsilon I, and then go in that direction with step size hi, same like gradient descent, right? Yi plus hi epsilon I. Adams-Bashforth is one method which takes epsilon I and epsilon I minus 1. So two previous neural network evaluations, right? You can store it. You don't have to compute, you can store it. So again, storage complexity is higher, I agree, right? So this method has storage complexity higher than first order method, right? So all these solvers which you generally see for solving ODEs assume that your velocity fields are linear. That is epsilon I minus 1, epsilon I plus 1 is in a linear direction, is connected in a linear manner. Okay, this is the basic assumption for any solver like Euler or Adams-Bashforth. Okay, and this is the problem as well. If you see here, yeah, so it has some advantage over Euler. I am going to skip that. If you see here, if we just blindly use Adams-Bashforth or Euler, as I told you, the prediction will be here and actual xti plus 1 will be here, because your velocity field can have variations and some variations can be large, right? So we need to move this point towards this true value, right? Obviously we cannot do it, we can only approximately move it, right? We don't know xti plus 1 beforehand, we are estimating xti plus 1. At least we should be able to find this direction. Okay? That's the main point, right? How do we correct? So what we do is, so we understand that all the ODE solvers assume the recent trend in the learned field is approximated linearly, right? So using the two previous field values, we can ask what would be the past history. What I mean by that is, we are at Ti, we want to move at Ti plus 1, right? We know everything about Ti and everything till Ti, right? We ask this simple question, if epsilon I minus 1 and epsilon I minus 2 is known, okay, the velocity fields at I minus 1 and I minus 2 is known, what would have been the linear prediction for epsilon I? Okay, so that is assumed as, that is defined as epsilon I extension. Okay. If it was linear, this would have been the actual velocity field at Ti, right? But then we also have the neural network output which gives you the exact velocity field at Ti, right? So what would be the difference is the question. The assumption here is the difference between epsilon I, the linear interpolation field, and the epsilon I, which is the original field, and epsilon I extension, which is assumed to be this linear. If it was linear, then we would have got this, right? The difference between epsilon I minus epsilon xt is the error at Ti. The assumption here is at Ti plus 1 also error will be in this direction. Okay. So you can think that the error assumption is transferred to the first derivative. Okay, instead of yti or yti plus 1, we are assuming its derivatives error, assuming that the direction will be same. Okay. You can use ASIN also, but again, right, it's a neural network. Yeah, it's a neural network. So yeah, still you can do some Hutchinson estimators and all are there. You can find ASIN. But here we don't want to go to that. Velocity field is for free. When I say velocity field, dxt by dt is for free, right? D square xt by dt square or the Hessian is not for free because you have to pass through the neural network, right? Back propagate to find out. Right? Yeah. So that's the assumption we do and we correct it. And turns out that correction helps us to get much better results. Yeah. So this is the defect epsilon I minus epsilon xt. And if a small delta I means your velocity field is nice, okay, the linear interpolation or the linear assumption makes sense. Okay. If it's high, that means the velocity field variations were too high and you have to correct. So we do that by adding gamma I hi into that defect. That's all. Right? Gamma is in our hand. Yeah, so it's still work in progress how to find gamma I properly. Currently we find that even a constant gamma I helps us. Right? So for the prediction we add this defect part back. So in effect from here we are telling that you move in this direction, correct in this direction. So we are going towards this true. hi? Hi is this, right? The time step, the difference. Hi. Rho ti plus 1 rho I. So, oh, okay. Gamma I 1. So the problem with gamma is you might overcorrect. So here, if you know the direction, if you put gamma I 1, generally it overcorrects, right? So we found that empirically we found that it should be between 0 and 1. In fact, now we know how to estimate that gamma I properly. I mean, we have a closed form, but in this work we have not added that, right? So if you put gamma I 1, it might overcorrect and it may go here. That is also wrong. So you should not correct too much as well, right? In fact, many of the existing solvers have this problem because they have come up with huge approximations, they overcorrect. And I will show one result that way. Yeah. So that's the algorithm. Any questions till now? So at the end what we did is we changed the variable, made the ODE much easier to work with, used a normal existing algorithm called Adams-Bashforth which uses two past velocity evaluations, and then we understood that algorithm and found what is the problem with that and corrected it, okay, with an assumption. That's what we have done till now, right? So again, in interest of time, I will skip this accuracy guarantees, which says that you don't lose anything by adding correction. So the algorithm once I want to go through. So you fix time steps t0, t1 to t capital N. T0 is capital T, that is you are starting with a Gaussian noise, and then T capital N is 0, you want to reach a data sample. Right? First you evaluate the model at xt0, okay, xt0 is a standard Gaussian noise, so you scale it as well because our OD was different, right? We need a scaled state variable, and then you calculate rho t0 and rho t1, sigma t0 by st0, it's basically noise to signal ratio, and find h0, which is the difference between in row space, your difference between two steps, two time points. And then first step you don't have any velocity evaluation, so the only thing you can do is Euler step, right? You move towards from yt0 plus h0 epsilon 0, and then you scale it back. Of course, you need to scale it back because yt0 was xt0 by st0. Right? Then from second you can start using the previous velocity evaluations. So you see here prediction term, I calculate the prediction terms by Adams-Bashforth to predictor and then correct it, okay, and then at the end scale it. So it's as simple as that. So there is nothing, no estimation required. The only problem here is correction weights. Okay, this is something which we have figured out only now, still work in progress, but we have found that even constant values work well. It has to be tuned per model, right? You give me Quen image, for that one value might work, for stable diffusion another value might work, because it all depends on velocity field, how the variations are. Yeah, so this is one result which graphically shows that at least in 6 to 10 or till 20, this black, red and green, which is our methods. I have not discussed this cap 2, cap 3. They are just variants. They have much better score. The lower FID, the better. FID basically says measures how natural the image is. Right. This is more interesting from the image point of view. What we found is that the integration, how you integrate the ODE is very important even to understand whether context in the image comes. This is an open problem. Actually, no one has been able to understand in diffusion models, after you learn a diffusion model, which time step is important for context, which time step is important for realistic, etc. Because we are using higher order solver, Adams Bashforth, we are able to find that this is in 6 steps, and here the prompt is stuffed animals looking at picture of other animals in the book. You see here in our method, the animals in the book is very clear, and note that here in all of this the model is same, only the solver is different. Solver used to, like the algorithm used to solve the ODE is different. But still you see in multiple cases the context is not clear, though model is same. Okay. As I said, trajectories can be different, right? Every solver will have different trajectory. So even here you notice that, I am not sure if it's clear, the 2 kids in pink and purple standing by a fence, the fence is clear, which is a context, is clear only in this method and in this method to an extent, but here there is a lot of noise. Okay, that's a problem. So this method cannot be used. All of them, these two are the best methods currently, so I'm just comparing with them. This is the difference. So this is in 10 NFEs. Previously the best solver were able to get something like this. Kits were okay, but the quality of the image was not as good. The context is much clearer here. We are yet to understand why the context is better in our algorithm. We are still trying to understand. There is something. Yes, context is depending on initial sample. How it is depending is something which we are trying to understand. Right? You're right, actually. So initially, when you start from noise, okay, how good your estimates is becomes very important. Right? Yeah. So yeah, these are some scores. Yeah, here one example where some of the methods overcorrect. So gamma I becomes very important. Currently we have kept as a constant. Ideally we should be finding what exactly gamma I should be, right? We need to, and again, right, we cannot use any complicated algorithm to do that. Then the time will increase, right? Yeah. So that's it for this talk. I want to conclude by saying that basically we discussed about diffusion models in a very different form. See, if you go and check these blogs, etc., which are 2-3 years old, they talk about Markov, non-Markov process, etc. For now, flow models and diffusion models are in a single framework, like how I discussed ST x0 plus sigma t epsilon. That's it. ST and sigma t will tell you whether it's a flow model or a diffusion model. So we clearly discussed about diffusion models and reached an ODE to be solved. And then we went into the ODE and understood what are the issues because of the velocity field variations, and we came up with a algorithm or a solver to solve it, right? Yeah. So the entire solver had 3 steps. Actually, first step is change in variables, which made the ODE easier to solve. Second is straightforward. There is nothing novel here. Okay, it's just using a existing Adams Bashforth method. But then the third step, which is correction, is about understanding how the trajectory moves, what is the error in trajectory, and correcting that at every step. Okay, it becomes very important because even one step you don't correct, it will accumulate and it will move on to the next step. Right? The errors will just accumulate. Limitations, yeah, there are multiple limitations. Already one I have told, gamma I. Okay, currently we have fine-tuned per model. Okay, we have found how to do that, but it's not very clear. So it's not right, though it's just one scalar coefficient, it should be found automatically and it should not be tunable per model. So that's one limitation. Another limitation is, as I was telling, people are thinking about sampling using 2 iterations, 3 iterations. Till 4, this method also don't work. From 6, it's able to get good quality, right? Because again, right, the correction is not correct, appropriate, exact, right? It's also an approximation. So even this correction approximation is not working if your step size is too high. It makes sense because the velocity variations, variations in the velocity field will be much higher that you cannot correct properly. So you need to come up with different method, which we have no idea about, right? Another problem is, as you rightly pointed out, right? In starting time steps, it might be important. So an obvious question is, how do we move from capital T to 0? Should it be T, T minus tau, T minus 2 tau uniform? Or should we change the time steps at which we find out the prediction, find out the state variable? Okay. We have found that you can actually change and get much better quality, right? But how to change, we don't know. So that's also a limitation and a future work. Okay. I think that's it from my side.
In the interest of time, can we take questions in the refreshment hut?
Yeah, sure.
Okay. Let us thank the speaker for accepting our invite and delivering a great talk. Refreshments are arranged at the coffee hut. Please help yourself. Thank you.